Hey, welcome to Ones and Zeros. My name's Ben, and today we're going to be taking a bit of a look at porting code in between various STM32 devices. Mainly so that if you have been watching some of our other videos working with the STM32 F7 Discovery or the F4 Nucleo boards that we've been playing with, and you've got a different device, different Nucleo or Discovery board or something like a Blue Pill or whatever, and you'd like to be able to use the code that we've been working on for that, we're going to have a bit of a look at sort of what it takes to grab one of our projects, one of our repositories from GitHub, for example, and actually start to get that code set up for the particular device that you want to be able to use it for. So in the case of today, the particular device that we're going to be looking at using, so we've got the F4 Nucleo board that we've been working with, and that's the code we're going to be starting with today, but we're going to be porting that over to this guy. So this is another Nucleo board, however this one is a H7 Nucleo144 board. And we could just look at porting over the F7 Discovery code to this H7 device. But to make things a little bit more interesting, we're actually going to take the F4 code and port that over to the H7. And much like our streams up to this point, the code from today will also be available up on GitHub after the end of the stream as well. So let's move that one out of the road. And we'll pop that one there for the moment. And let's jump over to this one. So basically starting with a bit of a clean slate at the moment. The only thing I've gone through and actually set up for this one so far is a GitHub repository for this one. Other than that, haven't actually done anything to go through and set up the project so far. So we'll close that. We have set up the folder for that one, of course, as well, just because of needing to set that up for the GitHub repository. But other than that, nothing in there at this point. So we're going to fire up a fresh copy of Cube IDE, and let's get this pointed at the particular folder that we're going to need there. So we'll create a new one for this one. Might help if I can type. First stream of the evening. It always takes a little bit to get the ball rolling. And we'll launch that guy there. Stream looks like it's behaving itself, which is awesome. And to all of the new subscribers, thank you so much for subscribing and following on Twitch and YouTube. It does mean a lot. It's cool to see that other people may be enjoying this stuff as well. So, all right, so we've got Cube IDE fired up, and we're going to go ahead and create a new STM32 project. Wait for this one to fire up the target selector for us. And to those couple of people watching, good evening or morning or whatever it is where you are. All right, so I'm going to jump into our board selector. We will select, where are we, Nucleo144 and H7. And this one is the 743ZI, so there is a newer version of this particular board available as well. However, I've had these ones for a little while, done a few different projects with them. So we'll select that one. I'm going to be targeting C++ for this one. And all of those settings look good. And just pop a project name in there for that one. Now, if you haven't worked with one of the this particular family before, much like any of them. So if you've got a H7 and you haven't used one of those with QBID before, or if you've got say a F4 and you haven't used one of those with QBID before, at this point it will go through and download the firmware package for that. Some cases it may go through and actually download an updated firmware package as well. Thankfully, that one's already sitting on our system at the moment, so we are good to go. Just wait for it to finish getting this set up for us. Excellent. All right. Now, we're not going to go through and bother setting up any of the stuff in here at the moment, because much like we've done, if you've seen the first episode of our Discovering STM32 series, I'm just going to close that guy, and everything is going to basically get done from scratch here, including going through and getting our drivers moved over, getting our core set up, our folder structure, all that sort of stuff. So try and get through this stuff relatively quickly, but try and cover some of the things that I think is important as well. So first things first is we are going to want to move over the particular drivers. So if we jump into you'll find if you jump into your user folder, there'll be an STM32 cube folder in there, a repository folder in there, and then you'll see all of the firmware that has been downloaded. So in this case, we want to go with the H7 firmware for this one. We'll jump into our drivers and we're going to get our HAL drivers copied across. Now, select all of those, unselect any of them that have template in the name because we don't actually need those guys. Just make sure there's none there that we don't want. And we're just going to drag that over to our include directory there. Tell it to copy the files. May as well tell it to override all for that one. Close that folder and jump back in here into the right window for that one, and going to do the same thing for our source files. Now there should be a few template files in here as well that we want to deselect. So deselect those guys, check that there's no others there that we don't want. Excellent. And move those over to our source folder there. Now the reason we do that is because by default only some of the files will be copied over when QBID goes through and actually creates the project. So in order to make sure that we've got the drivers for all of the peripherals for the HAL ready to go, copy the whole lot across, and that way even if we don't use all of the peripherals, they are there if we choose to use them for a project down the road. Just makes life a bit easier moving forward. Much like what we did with the F7 Discovery project, if most of these files in here we are going to throw away effectively. We are going to keep syscall, sysmem, and the system there, but we're going to move them into core. I like having all of the files visible together rather than having the inc and source folders there. We're going to leave the other ones here for the moment because those ones are going to get deleted. So that way we can just delete the two folders and it will make life a bit easier for us. And while we're in here, because we've got to change some of where our include paths and things are, we may as well go through and actually get our folder structure set up as well, similar to what we've got for, this is the F4 Nucleo code that we're basically going to be porting from. So we'll see we've got our QA drivers, QA systems, QA tools folders there. And this is kind of a bit of an example of how we're going to be laying out the files in the core directory as well. So just going to pop him onto my other screen for the moment. And let's go through and get some folders created. So we want QA drivers. Might help if I actually create a folder rather than just a file. That'll be QA drivers. QA systems. I'm keeping all of this consistent with how we've done the F4 and F7 source code as well, just because it does mean that it will make life a bit easier for moving in between the different code bases so that everything's fairly common in between all of them. Now we're just going to right click on our project itself, jump into properties, go into C++ General and open up our paths and symbols and get our folders set up in here. We're going to do check our source locations are set up correctly. So that's good for those ones. Also going to want QA systems in there and QA tools. Do that for our release config as well. Like so. And then for this one, we're going to jump into all configurations. Unfortunately, can't use all configurations when we're doing the source locations. Unfortunately, it would be much simpler if we could. And in here, we are going to pop in, just going to go with core, and we'll delete that core inc in a moment. Also going to want QA drivers, QA systems, and QA tools. And this one we can get rid of. We're going to do the same thing for our GNU C++ due to the fact that we're going to be using C++ for the code for these guys. So core QA drivers, QA systems, and QA tools. And I'll apply that. Excellent. And that's got that bit out of the road. Now it's a matter of getting our core folders moved across, or core files moved across. So for this one, we're just going to open up our Quartz Arc folder here, go into our F4 code that we were looking at in QBID before, and go into core, and we're going to copy all of these guys into there, like so. Also going to copy our HAL configuration into there as well. Now, there will be some differences in between the different device families. If you were porting from, say, one F3 device to another F3 device, for example, it's going to be fairly similar. There will be some peripherals that are in one device that aren't in the other. When you're going in between different families of the STM32 devices, there is a little bit more changes in between the devices, especially if you're going from, say, an F4 device as we are to a H7 device, because they're internally quite different. We're going to have a look in our main C folder. So this is the one that was actually generated by QBID when we created the project. And there's a few things that are worth taking note of here. One of them will be some of the items that are in our system clock config, because the clock config for this device is going to be a little bit more complicated than the clock config for, say, our F4 device, due to the fact that there's more peripheral and host buses in this particular device. So we've actually got 4 peripheral buses as opposed to the 2 that are in the F4 device. There will also be some other bits and pieces. See if I can find an example of that. Where are we? Not hiding at the moment. But anyway, just so you've got a bit of an idea of that, let's go ahead and delete these folders and the files that are inside them, like so, and we'll open up our main.cpp, our setup.hpp, and we're going to open up our HAL configuration. Also going to need to make some changes to our boot.cpp file as well. These are going to be the main ones that we want to get done to get the system up and running. Once we've got all of that done, we've got it booting correctly, we are going to go through and look at getting the user LED set up so that we can actually test and make sure that we're actually getting code running properly. So as long as we can get an LED blinking, then be fairly happy with that. And then in the next stream of this type, we'll go through and we'll start getting some of the drivers moved over that we've been working on. So things like our serial driver and serial system, so that we can communicate with the serial terminal on the laptop, as well as the external interrupt and timer code that we've been working on as well. So this one, we just want to get the initial project up and running, make sure that things are running correctly on the device. So jump into our HAL configuration, and let's go through and enable some of the various HAL modules that we know that we're going to be using. There is some that are enabled already. We'll just go through and double check if there's any that aren't already enabled that we're going to want. We've got UART. We're going to want timers, definitely. Probably going to be using SPI, so we'll pop that one in there. Probably going to be doing some stuff with SCI moving forward. Random number generator, real-time clock. We might go with I2S as well, so that's something that I want to get into in future. And fairly happy with that for the moment. It's worth double checking this stuff now as well, because if we do go to use a particular device with the HAL that we haven't enabled in here, you will get build errors when you go to compile it. So it's worth double checking that. One of the other things that we're going to need to do, excuse me, is if we jump into our setup.hpp, with the way we've set up the projects for the F7 Discovery and the F4 Nucleo board, the only places where we are including files related to the specific device or the HAL is in the setup file. And the reason we've done it that way is so that this is the only place we're going to have to modify those in order to be able to get access to those things. And we're not going to have to go and run through and change that in a bunch of different files. So in this case, we're just going to pop in H7 there, which should make it happy with both of those. And while we're in here, we might actually go through and get... We might comment this out for the moment, because we'll worry about that with the next stream. But we do want to actually go through and define the particular ports for the 3 user LEDs that are on this board, as well as for the user button. Now for that, we're going to jump into the datasheet library that I've got. Definitely recommend keeping copies of all of the data sheets that you use for any of the boards or devices that you've got, because that way it saves having to jump onto the ST website anytime you need to go hunting those down. And if we jump into here, we'll see we've got the Nucleo user manual, which should have the particular bits that we're going to want in here. I think it's in this one. Where are we? Maybe it's not this one. Let's see what else we've got here. Not that one. Not that one. Definitely thought it was this particular one. Where are we? Oh, there we go. Board functions. So we can see in this document it does actually specify what the user LEDs are for the green, yellow, and red LEDs, as well as what pin the user button is connected to as well. So if you're hunting for that, that's in the user manual for the particular board. You will find that also for discovery boards as well. It's going to be a fairly similar thing. So we'll pop that across onto our other screen there. And let's get these guys changed. So I'm going to pop our green one in there. So that one is on port B0. And we've got our yellow one. Which is on port E1. And we've got a red one. I do like the fact that this board has more user LEDs than, okay, that is port B, than just the single user LED that's on the Nucleo64 boards. Does make life a bit easier when, especially as far as troubleshooting and just general flexibility as well. So that's on B14, and then our user button is on C13. So that's actually the same as the Nucleo64. Okay. Wonderful. All right. Just double checking I had those guys correct. And that's basically all we should need to do in the setup. And then it's going to be a matter of getting some of the stuff changed for actually initializing it. As I mentioned, there will be some differences in between devices, especially going between the F4 and the H7. So with this one, where's the particular bit I want? Alright, so I'm going to need to enable our caches much like we have here. However, do it a little bit differently as far as doing it for the H7. It's actually a bit more like we do it for the F7. So enable iCache and enable dcache. So our instruction cache and data cache respectively. Get rid of those guys. Fix up our okay. Our indents are going to be messed up as well. So anyone that's seen the episode 1 for the F7 Discovery series, I will have mentioned in there that I'm a bit of a fan of 2 space tabs. Do prefer that as opposed to the 4 space tabs that it has by default. And in here we should have, where's it hiding? So we're going to need to modify that in here. Just change that one there, and we will need to rename the profile as well, otherwise it's not going to allow us to save it. So that one, and then we'll also need to modify, if I can remember where it's actually hiding. Had trouble remembering this one last time as well. There we go. So change our displayed tab width. Like so. And if you do prefer to have those set up with 4 space tabs, you can just go through and change those settings in those 2 particular places as well, and it'll be good to go. By changing it in both of those places, it not only fixes it up for any code that you write moving forward, but it will actually go through and fix it up for all of the code that's currently existing in the project as well. So kind of gets it fixed up properly with both of those. So we've got our caches enabled. The next thing is normally you would go through and go HAL init. However, so that we can actually see what is actually being done a little bit better, if we go through, we'll right click on that and go open declaration, you will find there's a few bits and pieces in here. And we're just going to actually go with the bits and pieces that we want. So in this case, we're going to grab our set priority grouping. As we can see, already got that one in there. And we're going to want our HAL init tick as well, which we already have in here as well. So I like to have all of the bits in the boot code that we're going to need in order for it to boot. So rather than calling HAL init, I like to have those bits directly in the code, because that way I can see at a glance what is actually going on in order to get the device started up, rather than actually going through and calling HAL init. Part of the reason for that as well is because I don't typically use the HAL quite always the way the HAL is intended to be used. I use it for helping to get things set up and tweaked and changed in ways that actually help me get code written quicker, without actually relying on too much of it. So in some instances, as you may have seen in previous videos where we're dealing with UARTs and things like that, I do prefer in some cases to just go with direct register access, or to use particular parts like macros and things that are within the HAL to retain a bit more control over what the device is doing while still leveraging some of the ability to get things done a bit quicker that the HAL allows. So now that we've got that bit done, we're going to go through and have a look at getting our oscillator set up. However, for this device, the other step that we're going to need to do is we're going to need to configure our internal power regulator as well. And a couple of steps for that one. So I'm going to pop these in here. And this is going to be a little bit different than the way we do it for the F4. I'm going to grab that guy and pop him in there. And change this so that we can use scale 0 for this one. And we're also going to call HAL power X config supply. And pop that in there. And we also want to make sure that things are actually ready to go before we continue as well. So HAL power get flag, power flag, so VOS ready. All right, that's that bit done. I'm going to go through and get our oscillator set up. So all of this is fairly similar. We're still going to be using a RCC oscillator in at type def. However, there'll be some different bits and pieces that we're going to be using in here. So we are going to use the high-speed external oscillator for the main system. We are going to go with our HSE bypass. That stays the same. We're definitely going to turn our PLL on and set the PLL source to HSE. However, we're going to have some different PLL values. This particular device runs at 400 megahertz as opposed to the 100 megahertz of the F4 that we're porting the code from. So change some of this stuff across. PLLP, in this case, we're going to pop 2 in there. Q will be 20. And if you're curious about how we come up with these values, I recommend checking out the episode 1 of the Discovering STM32 video that we've done as well, but I will also go over that quickly in this one. So just quickly get these guys done. Maybe a few other bits that we're going to want in here as well. So PLL RGE, the RCC PLL 1, the VCI range 3, RCC OSC init, and you can also have a look at some of the example code that's supplied by ST as well, because you kind of get to see how different families of devices get set up a bit differently than each other there as well. PLL1, VCO wide, and last but not least, PLL frac N will be 0. So as far as figuring out the particular values for that, we open up our IOC file, which will bring up our configuration tool again. Okay, we jump into our clock configuration, and easiest way to get a bit of an idea of the particular values that we're going to need in here for our M, N, P, Q, and R values for our PLL. And also, if you're trying to figure this out for the other PLLs and figure out various pre-scalers as well, is you can just go through and actually pop in the particular value that you want into one of the boxes and then get it to actually calculate. We're not going to do that at the moment because it will go through and take a little while to calculate the different values, but just gives you a bit of an idea of how we'd go about that. So we can literally just pop in 480 megahertz, for example, into that particular box there, and it will go through and calculate everything else in order to get it set up to supply the particular frequencies that we want. And then you can just copy the values out. I prefer to do that rather than actually using this to configure the stuff for us, because again, we end up with the rather messy code that happens as a result of the CubeMX actually trying to configure everything. So we'll close that, jump back to that particular perspective, and we'll get our files open back up there, close our hal.c, and finish configuring this one here. So we've done our PLL. We're going to go through and actually configure our CPU and bus clocks now. There's a few additional ones that we're going to be wanting to worry about other than just these four. So basically our clock type in here is basically telling it what clocks we're actually looking to configure. So H clock, sys clock, P clock 1, P clock 2. We're also going to want in here our D3 P clock 1 and our D1 P clock 1 as well. Clock type D1 P clock 1. Our sys clock source will be still a PLL clock. Our AHB clock divider, we're going to go with div2 on that one. Our APB1 clock divider will be div2. APB2 will be div2. And then we've also got APB3 and 4 on this device because it's got a more complex clock structure effectively, or a more complex bus structure. And these guys will also be div2. If you're curious at sort of getting a bit of an idea of how the internals are laid out for the various devices, if I jump into our documentation here, from all of the STM32 devices on the ST website, you will find a datasheet and a reference manual for them. If you open up the datasheet, we'll open that up for the H7 and the F4 that we're porting from. So that'll be that one there. And there's a few handy bits that you'll find in here. If you've not had a look through these particular documents before, I definitely recommend getting a bit familiar with them because you will find some really useful information, including the pinouts and pin description, memory mapping, and the functional overview, things like that. There is also, in the reference manuals, really good breakdowns of how to actually use the particular peripherals at a register level as well. And even if you are using the HAL, it's really handy to know how things actually function at a register level, especially if you're going to be using the debugger in the Cube IDE, because if you go in and actually have a look at the devices as the system's running. And so you pause it at a breakpoint or just manually pause it. You can actually go in and see what the register values are for different parts of the system, different peripherals and things like that. So if you've got a bit of an idea of kind of how that stuff works, it does make the whole debugging process so much simpler. However, if we jump into our functional overview and scroll down a bit, should find the particular bit that I'm looking for. Or maybe it's in description. Yeah, there we go. So this is kind of the block diagram for the F4 device that we've been working with. So you can see there is still a bit going on. We do still have our host bus and our two peripheral buses, a bunch of peripherals and things in there. However, it's a little bit different when we go into our H7. If we jump in here and have a look at this one, it's quite a bit more complicated, which is why we've got to go through and actually set a little bit more stuff up for this one as opposed to the F4. So you can actually see there is 4 separate peripheral buses in here. You've got an AHB bus matrix as well as the AXI bus matrix. And the routing and DMAs and things like that are a decent bit more complicated as well. But that's kind of the trade-off that you make for being able to use a device that's a bit more powerful. If you were to pull up the diagram for, say, an F1 device, it's going to look a lot more like the F4 diagram itself and be quite a bit simpler. If we had a look at the diagram for the F7 that we're using on the discovery board, it's going to be somewhere in between this H7 and the F4. So it's worth getting a little bit familiar with these diagrams as well, because not only does it give you a quick overview of what peripherals are actually in the device that you're using, but it does sort of give you more of an idea on a visual level of how things are actually laid out as well, which again, knowing that stuff can make life a little bit easier as well. So we've got our CPU and bus clocks sorted out there. And I'm not going to bother with our peripheral clocks for the moment, but we are going to go through and actually set up the GPIO port clocks or get those enabled. So in the F4 that we've been working with, there's only 4 GPIO ports. Now we have a few more in the H7 that we're working with. So there's another 1, 2, 3, 4, 5, 6, 7. So it's actually A through to K on this particular device. Like so. And that is our basic boot code ready to go. Let's strip a few things out of here for the moment. We're going to keep our GPIO because we are going to port across the GPIO driver during this stream as well. However, things like our UART and our external interrupts and stuff, timers and stuff, we'll get that done during the next stream for this series. I'm going to keep our task timing and everything the way it is. I'm going to change this because we're going to use our green user LED as our heartbeat. So may as well rename that one. Get rid of this code. And basically just want our processing loop with our heartbeat LED update in there. We need to rename this one. And it all looks good there. And then we'll just get the GPIO driver moved across as well. So again, if we jump into the source code from our F4, jump into our drivers and grab our GPIO drivers. Pop those in here, copy those across. And for these ones, because of the way we've been doing the code for various things, it's fairly portable between devices, so we're not really going to have to change too much. There will be certain things that will change. So for example, the particular registers that we access for TX and RX for the UARTs will be different. So the F4 device has just a single register called DR, or the data register, that it uses for both TX and RX, whereas if you're dealing with a F7 or H7 device, it actually uses a TDR for, or transmit data register for transmit, and a separate RDR or receive data register for receiving. But we'll see how we modify that during the next stream for this series as well. So we'll jump back in here. We'll make sure we're popping in the right port and pin for this one. So the ones that we popped into our setup file. So this guy here. And let's see if that will build for us. This first build will take a little bit longer, simply because it's going to go through all of those particular HAL files as well. And while it's doing that, let's get our board connected. So 3 errors. Where are we? That'll be in our handlers file. Oh, okay. So I need to strip some of this stuff out of here that we had in the F4 code that we're not currently using in this code, including these interrupt handlers. And we'll remove those from our HPP as well. The other thing that you'll notice will be a little bit different between different device families too is if we jump into our startup file, there is quite a lot more IRQ handlers for this particular device. You'll notice if we pull up the F4, drag that one over there. So you'll notice there's quite a few of these IRQ handlers that are 0 and don't actually have a particular handler associated with them on the F4, whereas a lot more of them are actually being used for the H7 device. So it's worth being aware of that as well. But other than that, there's not that many changes in between various device families, which is really good. It's one of the reasons why I find the STM32 series so flexible. So it doesn't matter whether you're going from an F0 all the way up to a H7 or anything in between. There's a lot of common stuff, and code is really quite portable in between the devices. All right, so that's built correctly. So we'll dump that over onto our Nucleo board. Go OK on that one. And of course we need a firmware update for ST-Link. Don't think I've used this board in a little while. So I'm just going to open that into update mode and do an upgrade on that, which generally doesn't take too long. So that stream's still behaving itself, which is good. All right, and it's reconnected the device, and we should be able to go ahead and pop the code onto the board now. Which we jump over to that one, has popped on there. However, we don't have a flashing green LED, which means there is something that we haven't done quite right. So let's figure out what that is. And what we're going to do is pop a breakpoint in here where we actually go through and set up our LED. And let's jump into debug mode and figure out why it's misbehaving. Switch to our debug perspective. And let's get it to jump up to that breakpoint for us. Something a little bit strange going on there. Wants to make things a little bit more interesting for me today. Always up for a challenge. Let's just unplug and replug that device. And let's try that one more time. Now I'm just going to step over system initialize. Okay, it's done that okay. It's done that okay. It's like we're possibly running into an issue with the data cache, of all things. It's still running and it hasn't actually stopped, even though we basically just told it to step over that. Let's remove the caches from the equation for the moment. See if maybe they're giving us a bit of an issue. It's part of the reason why I like doing the streams, doing this stuff live, is because that way you get to see the particular approach to solving these sort of strange problems that you're likely to come across at some point as well. So we'll resume that. You see when we resume that, it should actually then get to this breakpoint and pause, which means there's something in the system initialization that it doesn't like. Which is a little bit random. Now, what we can do, just to make sure that the board itself doesn't have an issue, is actually take some old code from another project where the H7 was being used, and let's just dump that on there and make sure that that works as it should, just so that we can confirm that the issue is definitely our actual code rather than the board itself. It's pretty unlikely that it's going to be a hardware failure, but it's always good to just rule that out. All right. And we now know that it's definitely an issue with the code because we have a flashing green LED. So let's pop that back across and let's be fairly certain at this point it's something that's going on in our system initialization that is causing the issue for us, mainly because it's not actually getting to this breakpoint when we go into debug mode. So it does help narrow it down a little bit. So if we jump back into our boot code, let's just go through and double check how things are being set up here. So caches, let's double check if there was anything there that we missed. We're setting our priority grouping, which is correct. Initializing our assistic timer, that's all correct. That's all good being done in that particular order. Power regulators being set up correctly. Let's pop a breakpoint in there. All right. It really wants to mess with me tonight. Where are we? That's all good, that's all good. Let's get rid of that. That stuff's all good. Let's just get rid of that. I don't think that'll be doing it. Got this error the other night. It was actually the virus protection, which I don't believe we've even got running at the moment. However, it has entered debug mode, which is even weirder. All right. And we have actually gotten to this breakpoint, which is good. Step over that, step over that. See if we actually get... Yeah, we get out of that while loop correctly, so that is all setting up correctly. Let's see if we get to our next breakpoint. Not getting to the next breakpoint, so likely something with our oscillator setup. We've got HSE bypass PLL on. Let's pop a breakpoint there. Terminate and relaunch that one. Resume it. Get to that breakpoint, no worries. Get to this breakpoint, no worries. Then what happens after that? So we jump into this one. We'll return from that okay. Wonder if it's that guy. Let's get rid of these breakpoints. And let's pop one in here for our clock config. So we know it was getting up to this point. Let's see if we can get it to get to this point. So we don't necessarily need the sysconfig clock to be enabled, which is why we'll just skip that for the moment. It's kind of a matter of detective work, and I find the biggest thing, I spent a lot of years when I first got into programming getting super frustrated with bugs. The best thing you can learn to do for yourself when it comes to debugging code is to stay as calm as possible and realize that it's all perfectly okay, because bugs are going to happen. No point getting stressed out about them. Okay, so we are getting to this point perfectly fine. Let's step over that. And we're getting to that same particular issue. Highly doubt it's going to be something to do with these guys. And the next breakpoint after that is this one up here, which is the very next thing after enabling the GPIO clocks. So it kind of narrows the particular issue we're having down to something in our clock configuration. So let's terminate and relaunch that. Actually, we'll also just double check these as well. Get it to run up to that breakpoint, which it has. Flash latency of 4, which is perfectly fine. Clock source is PLL clock. We are missing a bit of information. So there is another bit of information that it actually wants for the H7 that we didn't need for the F4, which is our sysclock divider. So let's terminate that for the moment and jump back into debug. Although there's plenty of things that I could potentially complain about with QByDE, the debug is actually not too bad. Okay, so we get to that breakpoint fine. Let's try stepping over that now. Still running into an issue. I'm guessing if we run that, it's still going to get to a point where it locks up. It certainly is. Alright, we'll pop that breakpoint back in, jump back into debug. It's like I have another follower on Twitch too, which is awesome. Thank you for that. Okay, we want to jump to that breakpoint. We're going to jump in here and let's see if we can find where it's actually misbehaving. So setting our flash latency, it's doing that fine. I'm basically just going to keep stepping through. See if we can find the point where it's basically deciding it doesn't want to behave. Sysclock config. Maybe something to do with Systic. Okay. Which we are setting up here. Which is all correct. Now, my typical rule for debugging is if you look over the code and you're not seeing where the issue is, you're looking in the wrong spot. And as much as that might sound like a really simple thing, it's actually generally tends to be something that is really apt for particular issues like this one. This is a bit of a fun one. Okay, just for the sake of it, let's just call HAL init and see if that makes a difference. Which it shouldn't, but maybe it might as well. No. Worth trying. Again, at this point, it's worth... The goal is kind of to gather as much information as possible about what it is or isn't doing, and trying to nail down where the particular issue is. So we have a vague idea of where the issue is. We know it's something that's going on in here somewhere where it's starting to misbehave. It could be something to do with our oscillator setup. However, we have been over that. Let's double check that as well. So 120, so M is 1, N is 120, P is 2, Q is 20, R is 2. PLL range is VCI range 3, which is correct. PLL 1 VCO wide for our VCO selection. And our N fractional is 0. HSC bypass oscillator in it. Oscillator type is HSC. That is all correct. Power configuration is definitely correct. And just double check the values we're giving it here, which is this clock, P clock 1, P clock 2. All right, now because it seemed to be stopping at our systic before, let's just double check. Where are we? So it is still just called systic handler in here, which is, I believe, what it's called in here as well. That's correct. However, maybe the HAL is slightly different in between these guys. So let's just double check that as well. Where are we? HAL inktick, HAL systic IRQ handler. So that is all the same as well. All right. Back into debug mode. Going to make use of that breakpoint yet again. Switch to that one. And grab some more coffee to refuel a bit. All right, let's jump to our breakpoint. Let's jump back in here. And let's step up to where we ran into that before. Each clock config is just up here. This was where we hit the error before. And yet again. Right. And that is actually quite interesting, because all it's doing in that particular method is reading from there. And that's enough to actually lock the device up and cause it to shut down. Super interesting. Never actually come across that before. Okay, let's get a little bit more interesting with this one. It's actually just making me want to kick its butt now, just for the hell of it. Alright. Now, we know we have code that works from the previous project that we popped on there before. So, just for the sake of it, let's just copy and paste all of the boot code from that as it is in that particular project, which is basically identical to what we're using. And let's see what happens. And if it does exactly the same thing again, then we know it's definitely not that we're having an issue with. So that's up to that point there, correct. If anything, it'll either rule out that that's where the issue is, or it'll show us that that's what the issue was. So one way or the other, we get to learn something from it. That all looks good there. Do we have an... Oh no, it's just a warning because we're not actually doing peripheral clock initialization. That's perfectly fine. Let's just dump it on there and see what happens. Unbelievable. We have a flashing green LED. So the code that we were using does actually have an issue in it, which makes it even more interesting. So let's jump back here and let's figure out why. because we could just call it a day at that. That's not good enough. We need to know why. Let's go to editor, vertical. Alright, so if we scroll down, we've got the particular code that we were working with, and we've got the code that we just copied in. So let's simplify this a little here. I'm going to uncomment this code that we're having the issue with. Get rid of our breakpoint. We're going to comment the code that we copied in. Alright, so enabling iCache, enabling dcache, both identical. The only difference here is that we're using HAL init instead of doing the priority grouping and systic manually. So keep it consistent with the other code, even though we did this before. It's always good to double check. We're just going to go with HAL init. Now, these are just declarations here, which we are declaring these down here, which is OS init type def and clock init type def. The names are slightly different, but that doesn't really matter. We're doing our configuration of our internal power regulator, which is identical. HAL power voltage scaling config. Power regulator voltage scale 0, that's the same. While not HAL power get flag, power flag ready, VOS ready, that's identical. Slater type, HSE state, PLL source, all the same. Our PLL values, which we double checked before as well, are correct. Our PLL range is the same. VCO selection, our frac N is the same. The only difference with our actual initialization is here we're actually returning fail, whereas in this code we're not actually doing anything. Now it's just a comment in there. Not doing our sysconfig here, a sysconfig clock there, but we've got it commented here anyway. Which brings us to this bit. So H clock, sys clock, P clock 1, P clock 2, D3 P clock 1, it's the same D1 P clock 1. Sys clock source is PLL clock, it's the same. Sys clock div 1. Found it. That should be H clock div 2. And there, I'd be nearly certain is going to be the particular issue. Let's dump that on there. That builds okay. It's because I clicked the button twice. Let's just do it again just to make sure. And we have a flashing green LED. So it's basically we were giving it the wrong value for our host bus clock divider. Wonderful. And just to double check as well, let's go through and instead of using HAL init, we're going to do our NVIC priority grouping and our SysTick manually the way I wanted to do them before. We know that that code there can be removed because we don't need that now. Let's build that and just double check that it still works. Run that. And we still have a flashing green LED. Lovely. So, could have been much simpler if I had have actually double checked things a little closer, but sometimes it can be pretty easy to miss something like that. So, not going to beat myself up about that too much. Hope that was fairly entertaining. So this yeah, exactly, Nuggy out. That is exactly what it was. So simply giving it the wrong value, it was popping the wrong value into the register, which was enough to lock the chip up in a way that I've not seen in the entire time I've been working with STM32s. So it was actually a pretty impressive crash for the chip to behave the way it was behaving. It's pretty cool. So this code will be up shortly after this stream, and then probably going to take a bit of a break for maybe half an hour, and then I believe we are going to be doing, can't remember which episode we are up to. I think it's episode 8 of the Discovering STM32 series, where we're actually going to be going through and doing some of the rendering code for our F7 discovery board that we've been working with in that series. So that is this guy right here. So previously been working on getting stuff done for that one. Get the camera to sit where I want it. So that will be coming up fairly shortly, and then it's quite possible that I'm going to push for a third stream this evening as well, where we'll be taking a bit of a look at doing some stuff with encoders, rotary encoders, with our F4 Nucleo board that we've been messing with in our STM32 Basic series. So that stuff will be coming up shortly. If there is any questions or anything like that, definitely feel free to pop those in. And again, Nuggy out. Thanks for sticking through that. I hope you found that nice and entertaining. I certainly did. Got to see a particular bug I've never seen before. And thanks so much for watching.